principle, we know now how to operate the user interface. But how do we create a mesh? There are two completely different meshing approaches: the conventional way, by meshing one body after another, and assembly meshing, which meshes everything in one step. As the name already indicates, the part or body approach occurs at the part or body level. Every body can have a different meshing method and can be meshed individually. If we have a multi-body part, we get a conformal mesh in the end. This approach is very flexible, but we usually have to clean up our geometry before we go to meshing. The assembly meshing approach meshes the entire model and creates always conformal meshes. There is no need to extract the fluid volume, and it can even walk over small gaps in the model. However, this comes at a price of high memory consumption and little control over mesh quality. We will look into this method in Lecture 7, because assembly meshing is not interoperable with the conventional approach. In this and the next few lectures, we will concentrate on the body-based approach. We have already seen during the presentation of the preprocessing workflow that there are several meshing methods available which create different types of elements. In 3D, there are 5 element types. The tetrahedral cell is very flexible. Everything can be meshed with tetrahedrals. Unfortunately, the mesh quality becomes quite bad if those elements are stretched even a little. The hexahedral is on the other end of cell types. It is quite unflexible, and the effort for geometry cleanup and decomposition can be very high. But they are far superior to tetrahedrals when the flow is aligned with the cell. They can also be stretched without losing too much element quality. For hybrid meshes that contain both element types, pyramids are required for the transition from hex to tet elements. Pyramids are very unpopular because it is easy to produce poor quality elements with them. A compromise between hex and tet elements are prisms. They are usually used in the boundary layer because they are as flexible as tets regarding the description of the surface, but they can also be stretched like hex elements without compromising the quality too much. The element type that is not on this slide is the polyhedra. CFX creates polyhedra automatically from a tet mesh. In Fluent, this conversion has to be applied manually. Polyhedral elements have usually a good quality, but are more diffusive than hexahedrals. There are multiple meshing methods for all those element types. The automatic method chooses by itself if sweep can be used to create hexahedrals or prisms. If this is not possible, it uses a tetrahedral method. Of course, we can manually assign those methods and have even more to choose from. Multizone, for example, can create hex, tet, and hybrid meshes. It uses the blocking approach from ISIM-CFD. And there is assembly meshing again, which creates all element types, but most cells are hexahedral. We will look into the different methods in detail in the next lecture. Here we see a few examples for the different methods. In the upper left, we see a pure tetrahedral mesh. Actually, we only see the triangular surface mesh. In the middle, we have an example for translational and rotational sweep, which creates only hexahedral elements in this case. In the upper right corner, we have a hybrid mesh with hex, pyramids, and tets, created by the automatic itself. In the lower row, we see a multi-zone hex mesh and a cut cell mesh created with the assembly meshing method. Of course, there are also 2D elements, tris and quads. Their characteristics correspond to tets and hex elements in 3D. In 2D, we do not have so many methods to choose from. However, the available methods are capable to handle 2D meshing quite well.